Okay, so I have 12:10, so I'm going to stop our session clock at 12:10. So we have 90 minutes from now. Um, Good afternoon. Thank you for coming. And this is the last session of the Easter meeting, last session period. My name is Bill Tang. I co-chair the Agriculture and Climate Cluster of ESIP, along with Brian Wee, who unfortunately could not make it this time. Um, we have Ellie Davis, our community fellow, helping us for the second year in a row, and she's really, really helpful. So today's session, the title is there, Fire Effect on Soil Morphology Across Time Scales. I just want to, before we get to the speakers, I want to just take a few minutes to give a little background for, I'm not sure if everybody is familiar with the cluster. So the cluster began in 2013, and shown on the screen are some contact information if you're interested to get involved. The listserv and the wiki page, and we have a monthly telecon every first Tuesday of each month at 3 p.m. Eastern. So some of the activities that we've been involved in since 2013, we began with USDA, not a surprise, with the LTAR network, with their climate hubs, and then we moved on to the USCRT, Climate Resilience Toolkit, developing some of the case studies. And we also had a short foray into UAV with agriculture. We did an ESIP lab project, data to decisions with climate resilience. And then more recently, we are venturing into the ML, machine learning in agriculture application realm. And yesterday, some of you might have been at the session, the planning session, the agro AI planning session. So the new focus area of this cluster. If you didn't make it to that one, there is a recording for the session. So these are some of the areas that we've been involved in. Most of them are still active, although not necessarily every one of them at the same time, just for lack of resources. So quickly, kind of the provenance of how this session came about. We, about a year and a half ago, in some of the telecons, so some of the people had an idea of doing a soil data standards session. And the discussion went on, and eventually, at one of the telecons subsequent, it became a wildfire effects on soils responses session idea. And that broadened into more beyond the soil, just the ecosystem, and also in the other direction, narrow to specifically some of the effects on hazards and the susceptibility to hazards post-fire. So we then wanted to do a session in the summer meeting last July in Tacoma. We couldn't move forward with that. We had some scheduling issues. So this is how we became, how this session came about. And we are, of course, also looking towards summer in this July in Burlington to follow up. So moving on, so the 4 talks today is shown here. We're allocating or budgeting about 15 minutes each, including a couple of quick questions perhaps after each one. So James McKinnon from NASA Goddard, Cassie Todd Brown from University of Florida, Gainesville. She'll be doing this remotely. Daniel Fuga, whom you just heard from Virginia Tech, although he's currently in Hawaii. So he's very early for him, also remote. And Daria Kirschbaum from NASA Goddard. So hopefully, if I did this correctly, if we did this correctly, the flow of the story, what we're trying to do with this session should be clear from just the title of the talks. And after the talks, which would be about 60 minutes, we'll have about 20-minute discussion period with additional Q&A, and then a wrap up and look ahead. Okay, so I'm going to hand this off now to James from NASA Goddard, talking about machine learning and mapping of wildfires. James. Hold on. I saw you open them all. Yeah. Yeah, I better I don't know, hit some wrong.
Yeah, I can start hitting buttons too.
Yeah. Yeah, proposed Dahlia then changed.
Oh, yeah, there it is. Thanks. Okay, hi everybody. Um, so I'm going to, well, looks like we got Excel going crazy over here. So let's see if I can close this. Okay, now we're starting. So I'm going to talk about some machine learning methods for detecting wildfires. Um, so I'm a computer engineer, not a fire scientist. So I work at the Science Data Processing branch. So I do work very closely with scientists. So um, what I saw was a lot of data and an opportunity to try to, train a machine learning model to do something that we're already doing with a physics model. But I'll get into why this is important later. So just as a quick outline, I'm going to go over some background of the project, some motivations, go a little bit into the design methodology of the models, and then some verification and some field work that I did to kind of show off the model. And then I'll get into some future work as well. So why machine learning? So they're very useful where underlying patterns may not be known. Now, a lot of times we have physics-based models that we could use, um, to pull information out of data, but sometimes it would be nice to use algorithms that we can just throw a lot of data at it and have it pull out those patterns for us. So NASA has large amounts of data, and so I was able to use this to do fire detection. So can machine learning be used to solve science problems? It depends. So sometimes, a lot of times, it finds patterns that aren't there. Um, Machine learning, there's this idea of overfitting, where you train for too long, or you have a biased data set, and you wind up getting answers that don't make a lot of sense. So we have to look out for that. But also sometimes allows for non-scientists to make interesting findings. I'll get to that a little bit later. So the motivations I think are pretty obvious to this crowd, but wildfires are bad. They pose a danger to life and property. And so it's something we'd like to be able to react faster to, or maybe model their spread a little bit better. Um, One thing I noticed was that the current fire detection algorithms are ground-based, meaning uh, they get executed on the cloud. The data has to get sent down from the satellite, get processed in the data center, and then we get answers. And so that works, but my question is, can we do better? Um, so for this problem in particular, we need autonomous and really low latency detection. So we want to be able to detect that a fire is there as quickly as possible. Um, and one way to do that is to actually take the processing, take it out of the data center and put it into a satellite and actually use onboard processing to do this. And so, embedded platforms in general aren't really great for this. And so kind of working around this problem was a big part of this problem. So just as some goals, I already kind of mentioned this. Can we build a neural network that detects wildfires? Turns out you can, and Goddard's actually been doing it for 15 years. Although their results are pretty good, they're not as good as modern attempts, just because they were not using GPUs to train their models. So I used Modus. Modus is a great instrument for this sort of thing. There's already an active fire product using the modifier algorithm that I can use to basically create a supervised learning data set. So I can have my input data be spectral data from Modus, and then I already have ready-made this fire product that I can use to train on. The downside to this is that this algorithm is intractable for embedded systems. Something that we have to keep in mind if we want to get the latency as low as possible and to do this processing on board. And we eventually want to generalize this approach for use in other fields. I mean, neural networks are useful in a number of fields. Just briefly mention that use Modus. These are level 1B calibrated data products that I'm using as an input to my neural network. This is an important point because on the satellite itself, we won't have that data product. This is atmospherically corrected data, and we have access to raw data, essentially level 0 data. And so we do have to think about when we design a model, is it going to be able to handle this sort of thing? And we've been able to show in other situations, such as hyperspectral data from the Hyperion instrument, that when you train neural networks, they'll actually work pretty okay with raw data, even with it not being atmospherically corrected. So we figured using level 1B data products here made our lives easier, and it was a okay abstraction here. The data is basically local to Goddard, so when I'm chewing through terabytes of data, it's nice to basically go as fast as your Ethernet card goes, which is nice. Um, and then augmenting data. What I mean by that is Modis has a lot of spectral bands. So I can pick and choose what bands to train a model on in order to um, basically create like an analog for another instrument. So if I want to just pull out thermal bands or thermal and visual bands, it's easy for me to do that. So I'll just briefly mention this. Neural networks are basically complex things made out of simple parts as interconnected processing units. Take data in and create like an output that's either classification or some sort of regression. They're basically used everywhere now. If you have a phone, your phone is probably doing neural nets at some point. And so why would I even try to use neural nets in this particular situation? So here's the main thing, and I've already mentioned this, is that they're really good at finding patterns in data. And so on the left there, I have basically how the modifier algorithm works. And so you can basically think of it as like a decision tree. You go through each step and say, okay, I'm gonna use this thing to reject clouds, and I'm gonna use this thing to reject false positive sun glint. And so each step of that requires a human to say, this is important, we need to put this in the algorithm. With neural networks, you just give it so much data that it tends to find these underlying patterns for you. Whether those patterns are useful or not is another story, and it takes a lot of verification, but I have found in my work that they're very useful for this sort of thing. And this little diagram right here is a useful way to kind of show people how machine learning works. Really, the traditional programming paradigm, you create the rules yourself, but with machine learning, you let the answers and the data speak for itself. So for training these neural networks, we use Python. Python's great for this stuff. We can use common AI frameworks such as Keras and TensorFlow for some of the more complicated stuff we wanted to do. Basically, these are high-level frameworks that we can use in Python to do really rapid prototyping. So I was not a machine learning expert before I started this project, and they're just using these tools. I got a lot better at it, and also was able to test things very quickly, which was nice. Also, it natively uses GPUs. If anybody's done any CUDA programming before, it's not fun. So being able to use a Python library to do this for you is pretty cool. There's a number of things that we did to sort of just make our model better. I won't really get into it that much, but one thing that is important later is sort of not biasing your data set is really important. So what we did initially is we just randomly picked fires and randomly picked non-fires. And so it's useful, but it is sort of biased. There's situations where there are false positives that look really close to fires, and you might not get that in your data set if you're just randomly picking, among billions of pixels. And so that's one thing we had to look into. I'll get more into that later. But just as some initial results, it worked really well. We had over 99% accuracy, at least on the validation set, which is the side part you set aside while you're training. And what was really interesting is if you look at sort of the first layer on a neural network, we kind of created this magnitude of influence graph, which what it's showing here is, given a particular input, how useful was it in picking a particular output? And so we see that there is a large influence from the bands that were used in the modifier algorithm, which makes a lot of sense because it's the algorithm we're using to create the training data. What's also interesting is there are some bands that are useful even outside the modifier data, outside the modifier algorithm. And so, those are paths we can go into in the future and research and see, what sort of information is the algorithm pulling out of these bands in order to, get better results. And so we did some large-scale verification. We ran the model across a whole year's worth of data, and we got some pretty good results. There's a lot of numbers up there, but the important ones, producer accuracy is basically saying if there's a fire in a pixel, what's our percentage chance that we'll actually find that fire? And so, above 97% is pretty good. There was a lot of false positives though. That's where that 7% number comes from, is that, given a fire detection, what's the chance that it is actually a fire? And so this number is bad. It was initially bad because of this randomization of picking, our data sets. And we got around this by actually running the model multiple times to try to find, where are these situations where we get a lot of false positives, like sun glint. we can go back and find sun glint and add that back into the data set in order to make our model more accurate. And so basic results here is that we learned the modifier algorithm, which makes sense. I mean, that's where our ground truth came from. And basically the important bands in modifier were important elsewhere, but we also saw some other bands were useful as well. False positive rates were high, but we were able to mitigate that through a variety of means by basically going back and looking at what was really creating, the difficult points, the difficult detections in our system. So now I'm going to get into, what should we do in the future? We basically took MODIS data and detected fires in it. Well, we're already doing that. So what's the point in that? But so we're actually looking into the future. How do we make things better? And so one thing I mentioned was, how do we create really low latency data products? And we could do that through a variety of means. One is maybe use GOES. GOES East has United States, North America data every 5 minutes. So if we're able to process that and immediately find fires, then that would be good. But there are some downsides to this because this is already done. Is we have 2 kilometer pixels in the thermal bands. So 2 kilometers is not great for pinpointing where fires are and where they're starting. So if we can use AI and machine learning to do super resolution, if by taking multiple frames over time, we could take that and create higher resolution fire maps with a latency as low as 5 minutes, which would be awesome. Next, the other step, the other direction that we can go in with this is do more granularity in detections and also be able to take advantage of like fusing different sources of data together. And so what I mean by that is we could, if we were able to create a constellation of CubeSats, so anywhere from a dozen to hundreds, the more the better. We can get these really low revisit times. And so if we have a low revisit time, then there's a shorter maximum time between a satellite seeing a fire and reporting it to authorities on the ground. And so what would make that even better is if we could move this processing into the satellite to make detections immediate or near immediate. And so that could take advantage of thermal imagers on CubeSats, coupled with visual spectrum, just regular cameras fused together. We started looking at this and actually built a test prototype. So I can't, this is a small project, it's an internal research and development project. So I couldn't buy 12 CubeSats and launch them, but what I could do is get a drone and build a payload and to do some field testing with this stuff. And so what we did was we built a payload that combined a thermal imager with a visual spectrum camera that fused it together, and we fed that data through a convolutional neural network in order to detect fires or not. The next step is if we were to continue this project is, can we do more than binary classifications? Can we do fire or beyond fire, not fire? Can we do, is it pre-ignition, is it flaming, or is it smoldering? So basically, can we look at intensity and use it and take that information, detect it with neural networks and feed it back into models, fire models for seeing where are they going to spread, where are high risk areas for fires, looking at maybe hyperspectral imagers on a CubeSat to figure out fuel load conditions. But all this stuff needs good data fusion, co-registered data sets, and money for building CubeSats. So I'll just quickly go through just basically the field work we did. I don't know how much time I have left. So this is the field campaign payload configuration. We actually took a DJI drone. We built a payload that includes a thermal camera, like I mentioned, visual spectrum, really just a Raspberry Pi camera, all hooked up to a Raspberry Pi. And so we actually wrote our embedded neural net implementation to run on this Raspberry Pi and flew it and did fire detection in real time in this embedded system. And I just have a video right here of us out in the field. So this is nearby Goddard. We worked with the USDA. They have a lot of research fields around there, and they generate a lot of biomass throughout the year. So we asked them if we could burn a big pile of it, and surprisingly, they said yes, you could. So we made a big pile that's about 10 meters on a side and lit it on fire. And we flew a drone over it on a variety of configurations, close to it, only 50 meters or so, all the way up to 400 meters. Also off nadir, 45 degrees, in order to build up a big data set for us to train on. And so this is just a sort of a crummy looking output of the IR layer, the IR data. And what we can do is look at hotspots in the burn pile to be able to figure out which parts are flaming and which parts are just smoldering. So just for some conclusions, there's a lot of major challenges to using machine learning, in particular neural networks, with science problems. They're hard to understand, so luckily finding fires and doing binary classifications is not super tough with neural networks. So the neural networks were not large. So you could actually inspect these neural networks. They're not completely black boxes. You can look at and see influence of weights to be able to figure out, what is it actually doing under the hood. But once you get to really deep networks, the kind of networks that it would take to do this sort of state of the fire and intensity determinations, you get these deep convolutional neural networks, which are very hard to wrap your head around. There's also a general lack of confidence in machine learning methods, which is getting better over time. It's getting to be obvious that it is the future for a lot of things. It's not perfect, but it's going to take a lot of research to figure out where it really works great. But the kind of cool thing is this progress can be made really quickly. This work was done over the course of a year. The tools are getting better, more or less. Google and Facebook has PyTorch, which is also really interesting. And there's always more data. NASA generates an enormous amount of data. And the sad thing is, a lot of times that data really only gets looked at once, maybe twice if you're lucky. So to be able to go back and use this wealth of data that we have to be able to build these models that can kind of enable, the next generation of this stuff would be pretty cool. So that's pretty much it. I just want to put some thanks up there. Worked with the scientists on doing the fire detections. USDA helped us burn stuff out in the field, which was pretty cool. And then the drone team that helped fly us, which was interesting, because they don't let civil servants fly drones for some reason. Okay, so that's it. Any questions? I don't know how much time I have for questions.
Question. Is this one on? Okay. Did you see a difference in spectral signature depending upon what type of fuel was burning?
So that was not something we looked into directly. We were dealing with huge data sets. I think I skimmed over it, but we were in the millions of fire territory. So there was probably, what we were hoping for was that there was a large variety of fires in that data set, so that we would get a very wide sampling of the different types of fires, because fires in Africa are different than fires in California, and it's nice to get a good wide spread of this so we can really teach the model what's going on. But no, we didn't actually look directly at that sort of thing.
Well, just speculating that you might be able to better tune the algorithms if you can tailor them based on the type of fuel that's burning.
Mm-hmm.
So an algorithm that works over San Diego probably will not work as well over Vancouver and vice versa.
So yeah, so that's the tricky part of designing a single model that works with everything. Once you so that's important is getting a big part of this project is having the subject matter experts there, like the fire scientists, to be able to tell me what are the things that we're supposed to look at. And so you can kind of build in this prior knowledge into your model. If you can do that somehow, as maybe adding extra inputs to your neural network, then you can go a long way. Just as an example, we originally just put in all the spectral information, which worked okay. But then we're like, well, what other information can we put into this? And we started putting in sun angle and instrument angle, time of day, because that started giving us information about sun glint. And then whether it's over water or not is also another very important piece of information. So yeah, it's definitely something we're looking into.
Good.
Well, we'll have time later on at the end of the session to have more extended discussion. So I think we should move on right now. Okay. Thanks, James. So with the mapping, now that we know where the fires are, even if it's binary, so the next speaker, Kathy Top Brown from University of Maryland, Florida, Gainesville, will give an overview on what happens to the ecosystem from the fire.
Thanks, Bill. Should I take the screen?
Yeah, Ali will make you presenter. Oh yeah, okay.
Hold on a second. In order to continue recording, I have to change settings on my computer. Okay. I actually am going to need you to walk through the slides for me. I can't project a recorded session from here without closing GoToMeeting, so it's going to be faster for me to just say next slide, I think. If you could call up the slides again. Sorry about this, folks. Thank you so much for this invitation and the opportunity to present remotely. It's the first week of classes here at UF. This is my first year teaching here at UF. So I was very distraught to be missing the ESIP meeting yet again up in Maryland. But I'm delighted to talk with you about the effects of fire on ecosystems. So next slide. So we heard a little bit about how we can detect fires in ecosystems. And so this is going to talk a little bit more on the broad effects of fire on the ecosystem. Can we move to the next slide?
Yeah, Kathy, we have your title slide on right now.
Right, can you move to the first slide? Yes, there you go. So I'm going to mostly be talking about these 5 different effects of fire on the landscape and the ecosystem. It'll be briefly going over the first 4 and then diving a little bit deeper into the near and long-term implications for carbon stock management on the land surface, which is one of my specialties. So if we move to the next slide, the first one we're going to talk about is the effect of human health on smoke. And I'm not sure how many of us have been on the East Coast during fire season, but it's becoming quite common now, especially in the summer, that if you're anywhere near the Western US, you may have a couple of smoke days. And smoke is harmful to breathe. Lungs don't like it. In particular, it's the fine particulates that tend to be the most harmful for human health. Most of the data sets around monitoring and responding to this are things like satellite imaging that we just heard about previously from James, and also ground monitoring stations that monitor air quality. Fine particulate matter is a very common metric for that. So next slide. Maybe something that is less common to think about is how ash and char that settle out from these smoke plumes affects the surface albedo of the globe. So in this image here, you see a caramelized snow patch that was caused from the recent Australian bushfires that are still burning over in New Zealand. So this is particularly impactful in northern climates or in high latitudes where you get these sort of standing glaciers that are very impacted by smoke deposition. And this can actually affect the global energy budget. So when you think about how to model climate change, where you choose to set the albedo for the snow fields can be related to the fire frequency that's in your simulations. So mostly the obvious monitoring data again for this comes from satellite imaging. It's a large footprint effect. So yeah. Next slide. So maybe a little bit less commonly thought about is how heat shifts the water, the physical properties of the soil itself at those locations. So hot fires make soil hydrophobic. So this means that it repels water. So in addition to removing the vegetation when you have a hot fire burning through a location, you're also shifting how water flows over that soil. So you're exposing a lot of risk for flash flood events because of the combination of this removal of the vegetation and the shifting of the chemical structure of the soils. Generally, this hydrophobicity is relatively short term, but it does mean that if a fire event goes through an ecosystem and then you have a large rain event coming in after that, like you'll frequently see in California, you can trigger certain landslide effects. And I believe that we'll have someone talking about landslides later on in this session. So the measurements for hydrophobicity of soils, this is a little bit more tricky. It's not something that can really be well evaluated remotely. So state of the art still pretty much is put some water on the soil and see how long it takes to percolate through. And there are formal protocols on watching water droplets disappear on soil for quantifying this. All right, next slide. So all of these are relatively negative changes. Fires also have some potentially positive effects as well. A fire-driven landscape has a very specific ecosystem where fires play a key role. So this is an example of burn severity in a pine forest. And on the first slide here is a low severity burn. The middle slide is a moderate severity burn. And then the third slide is high severity burn. And you can see that you've got three very different ecosystems that are emerging with succession from these burn events. There are certain species that require fires for propagation. Certain pines in Florida are adapted to only propagate after a fire event that opens up the canopy and allows the saplings the most advantageous competitive strategy because there's no understory anymore. So fires are not necessarily a bad thing when you're talking about how that interacts with the local ecosystem. So related to this, if we move on to the next slide, is talking about how fires interact with the carbon cycle for long-term carbon management and trying to understand how atmospheric CO2 levels are going to change moving forward. Next slide. Right, so when we model the land carbon stocks, we typically think about splitting up the carbon between a vegetation and a decaying pools. So in a typical land carbon model, you'll split carbon between soil, litter, moss. We were looking specifically at a northern boreal climate, so the moss biomass was particularly significant in this ecosystem, and trees. So on the right side is sort of this normalized carbon stock, and you can see that most of the carbon in this system is stored in the soil and the litter pools, followed by the tree biomass, and that only a little bit of the biomass is stored in the moss, even though it's responsible for a lot of the photosynthesis that goes on in this system. So what we wanted to ask with this particular project was how does periodic fire events interact with the average carbon stock over long periods of time? So you could use this information to try to manage an ecosystem where you wanted to sequester carbon from the atmosphere into either your soil or your vegetation biomass. So with next slide. So we took a fairly typical mechanistic first order decay carbon model with those four main carbon pools: the tree, moss, litter, and soil pools. It's first order linear mathematically speaking because the carbon leaves the pool at a rate that's proportional to the carbon that's in the pool. And all of this is being driven with a net primary productivity trajectory. So we prescribed how quickly these trees and the moss were growing based on how long it had been since the last fire event. So if you go next slide, on this we overlaid some burn pools. So burned carbon decays slower than unburned carbon. It changes the chemical properties of the soil, producing biochar, and this is thought to stick around in the ecosystem longer. Now, with this model, we assumed that the more burns that the carbon had been through, the more recalcitrant it was. So if you had only burned once, you were maybe only half as recalcitrant, I'm sorry, you were maybe twice as recalcitrant as your unburned carbon. And if you had burned 3 times, you were a 3-fold increase on your recalcitrancy in your carbon stocks. So with the next slide, so we added on top of this a burn model. So lots of arrows here that basically say that most of the carbon was taken from the vegetation and the soil and litter pools and put into the burn pools. Some of it was blown off as carbon dioxide, which is generally, when these models are constructed, you're only tracking the amount of carbon that's burned as carbon dioxide. You're not tracking how the resulting biochar interacts with the decomposition. So next slide. So we took this model, which we called the grow, burn, decay model, and we used this to look at, to run a number of simulations forward and to do a sensitivity analysis to see where what's our most impactful parameter and where can we get data to influence the performance and to better tune these models based on these impactful parameters. So if you go to the next slide. So this is what a typical run looked like. So this sawtooth pattern that you're seeing here is the ecosystem recovering and then going through another burn event. So you can see that the first burn event converts a large portion of your soil carbon stock into a burn cohort. And then as you subsequently move along down your timeline to your next burn event, you're recovering your tree and your moss biomass, and you're losing your burn cohorts as that does have some interaction with your decay. So what we wanted to do is, because we're doing a parameter sensitivity, we needed to come up with some metrics to evaluate the performance of different parameter combinations, and the ones that we chose are on the next slide. So that little black line is the same black line that was shown previously, only projected forward in the future so we could see what the recovery time is. So there was a percentage of that carbon that was lost due to burn events. Eventually the system equilibrated where it started recovering that carbon because of the reduced decay from in the burn pools in this model. So the time to that minimum carbon stock we called the burn-in period. And then we were very interested in how long does it take your model to recover? How many burn events do you have to go through until your forest has the same carbon stock that it would have before you started burning the ecosystem? So if we move to the next slide. So this is a bit of a busy slide. On the x-axis here are the fraction that remains in the ecosystem after a burn. So you can think of this as the the intensity of the fire. So a high intensity fire will have less carbon remaining, and a low intensity fire will have more carbon remaining. On the y-axis is the carbon recovery time. So this is how many burn events do you have to go through until you recover the carbon that you lost in your from your initial burn-in period. The subgraphs progressing column-wise is the decay burn modifier. So a burn modifier of 0.1 was a very strong effect of burns, and as you get closer to 1, so 0.9, that was a very weak effect. Similarly, with the reburn potential, we assumed that biochar was less likely to burn than unburned carbon. And again, 0 is a very strong, or 1 is a very strong effect, and 0.9 is a very weak effect. And then finally, we also looked at fire return intervals. So how frequently does the ecosystem undergo burn events? In general, unless you had a very weak burn modifier, or this was not very influential. So something to notice here is the orders of magnitude on your y-axis for your land carbon recovery time. We're talking about 10 to the 10 number of burns in an ecosystem that you have to go through in order to recover the carbon that you've lost for some of these parameter combinations. So that is not in a human time scale, as it were. These burn events, especially in the boreal zone, only happen about once every 10 to 70 years. So 10 to the 10 is beyond the time scale that you're interested in as a land manager. However, if you have much stronger burn protections, below 0.05, you start getting into more human timescales. So some of these simulations recovered their land carbon stock in only 1 or 2 burns. So this particular parameter is really, these 2 parameters, both the burn modifier for the decay potential and the burn modifier for the reburn potential, are both critical to characterize for this type of mechanistic simulation. Next slide, please. Right, so these decay rates, really the only way to get at a decay rate and the modifiers for that are incubation studies with this type of model. There's really not a very good way to measure it either chemically or spectrally to get at how the decay rates shift with burn. Similarly, when you look at reburn rates, a pyrogenic index, so essentially combust the soil and see what temperature it combusts at and track that as a function of the number of burns the soil has seen, is again really the only way to try to get at that type of data. So aggregating multiple incubation studies and multiple pyrogenic studies across soil research projects can be really, really tricky because it's difficult to generate those metadata sets. Of course, in this type of full carbon model, a complete characterization of the living biomass, the litter pools and the soil pools is kind of the holy grail that you're frequently after as a modeler. That's very difficult to get at. And then in addition, for this new model, we're interested in biochar characterizations. And something that I didn't mention is the possibility of ash runoff after a fire event, that the amount of biochar doesn't necessarily stay at a given location, but as far as a carbon stock management program is concerned, it doesn't matter as much whether the biochar is on the location or if it runs off into the local watershed, because in both cases you're removing that carbon from the atmosphere and you're sequestering it in an ecosystem somewhere. So next slide. So with that, I'd like to say thank you. This fire model was developed in conjunction with Jennifer Bolzer up at Wilfrid Laurier University and Merit Turetsky at the University of Guelph. They have an absolutely gorgeous chronosequence of burn burns in the boreal zone that I almost presented instead of this. And acknowledge my funding agencies for this work for the Tides Canada and the Government of Northwest Territories. So with that, I'll take any questions. Thank you.
Thanks, Kathy. I think we have time for one quick question. Anybody have? Not, I'm going to hold mine until the end. So I'll come back to you, Kathy. I'm going to move on for the time being. So that's an overview of effects of fire on the ecosystem in general. So the next speaker, also remote, will be Daniel Fuka from Virginia Tech. So he's going to be talking about the effects of and also the effects on topography from wildfires.
Aloha, thank you very much. This is Dan Fuka, and let me get into presentation. Just with a quick oral confirmation, you guys see the slides, I hope?
Yes.
Excellent. Okay, so I got really jealous of everyone else's shorter title, so I have retitled mine to just Rapid Recharacterization of Watersheds. We're really focusing on the soils here, but as the last talk demonstrated, wildfires and forest fires tend to rapidly recharacterize the soils, and with that, we want to be able to recharacterize them as fast as possible for various reasons. This is a joint effort between Virginia Tech, OpenDAP, UMES, and USDA ARS, and it's funded by two consecutive National Science Foundation EarthCube Awards. One was the B-Cube project, as well as the current brokering project, Balto, that we'll get into. So why? Things really change after a forest fire, or at least can really change after forest fires. And so there is a need for rapid, consistent, and replicable initialization for basins. Everyone is probably familiar with seeing the risk of storms after forest fires causing landslides and water quality issues. So our existing soil characterizations really need to be rapidly extended within an area for hazard mitigation. And we need to really have the ability to seamlessly support very new data. That is, collect data and be able to throw it into our analysis very, very quickly and our recharacterization very quickly. In this, we want to allow maximum flexibility, and that is be able to support any type of analysis package, as there is many models for post-fire hazards, as well as pre-fire hazards and watershed water quality modeling. And our intent here is to complement rather than replace existing tools. This is, we want to support the tools that are used by these modeling efforts and just decrease the data wrangling that has been described as 80% of most analysis projects. So very quickly, forest fires, landslides, they are very well described in the literature. So it seems like it's a good use case to go after. And as far as landslides are concerned, they're also very dependent on the soil systems that are within an area. So I'm going to go into the purpose of the talk that was requested, which is actually in the soil genesis portion, which is frequently driven by hydrology. And we're going to discuss this little thing over in the upper right-hand corner, that this is a topographic index. And what a topographic index is basically a hydrological conductivity-based potential energy, utilizing the upslope area draining through a certain point That is everything that contributes water to a specific point in the basin or area of interest, and divided by the local slope of that point. So if you can think of a very large contributing area with a very flat surface, you can imagine that you would have deposition or something like that. And what we have found in our initial analysis, this is actually going through and getting a bunch of soil pedon data and mapping it and extracting these topographic indices in which we actually classify them because they have a very wide range. But if we classify them into 10 classes, we can see that we get fairly accurate representations and correlations with soil depth and as well as the texture, say sand or clay. That is, gravity and physics works. If we're going to describe this graphic here, basically the soils are deeper where the topographic index classes are higher. That is, the water is moving soils downhill. And then on the other side, you see the sorting that happens. Larger particulates are harder to move than smaller particulates. And something else that we utilize is the concept of pedo transfer functions, which allows you to take, and I'm going to point towards the right-hand graphic, but because we're going to look more heavily at saturated conductivity as one of our example hydraulic properties, and that is, if we know now the sand, silt, and clay is more at a higher resolution spatially, we can also start pulling out other of the watershed characteristics, of the other soil characteristics. So we can extend these pedo transfer functions to redistribute coarser resolution soils information. That might be handy when you go into a fire burn area. You want the highest resolution information that you can get. So those pedo transfer functions basically allow us to fill in the gaps for any of the hydraulic properties of the soils, as well as where there is potential for more soil carbon, less soil carbon, or for soil carbon to accumulate. Soil carbon, as previously pointed out, is fairly important. We have to build a workflow that is how, and this workflow is based on how high resolution spatial watershed models are initialized, because that is the basis of our research that we want to extend into this area that we're discussing today. But the basic thing is the standard workflow. People download DEM, and in our case, we want that process to be automated and easily updatable in case a new DEM is made available from like a drone flight. There's the watershed delineation, and we're using a very popular tool out of Utah State University, David Tarbotten's Tau DEM. We have the land use download and soils download, and then we do a soils recharacterizing because the soils information that we have to start with is the best information that we have to start with. So we recharacterize those soils and extend them to a much higher resolution using the topographic index. And then, of course, for modeling purposes, we also integrate historical and forecast weather data relatively quickly. To do this, the previous operational version was based off of a closed source brokering code. And so this project is actually based off of that and taking that and building an open sourced brokering platform. And that is what I had referred to before as Balto, the cyber infrastructure for distributed brokering. And we're really looking and interested when we're doing this on the right-hand side. Basically, we want what appears to be one data center or one data service that can point to many different data centers and data services. Because in this case, we're actually utilizing information from many different federal agencies, from USDA to USGS and National Weather Service, as well as other historical climatology services. So we're really looking at this, having a system that can make many different remote data sets appear like they are local. So where have we been, and where are we going? That is, we currently utilize, based off the old brokering system, we have access to be able to make appear local or off of one service many different elevation land sources. This is a system that we wanted to make sure could run in Africa as well as throughout the United States. The land use, soils, both globally as well as the best available in the United States. And then, of course, the historical weather data, we utilize a hourly database, which is the CFSR gridded data out of NCAR. And then we also have integrated forecasts just so that we can get into that concept of risk and how does a watershed and possibly other systems respond, and what is the risk of, say, a landslide happening is a potential use of that. So going back, we also want to discuss being able to put in new data, and that is this service that is running locally or for this for a specific purpose. Anything that can go into standard NetCDF files, HDF files, ASCII tables, and SQL databases can also be integrated relatively rapidly and also be made available along with those coupled and linked remote data sets. So in this case, if we just look at the digital elevation model, it's very common for after wildfire in an area that might impact humans to go and fly and get new LiDAR at much higher resolution. And that information can be thrown in generating and having access to a much higher resolution DEM and oftentimes a more accurate representation of the digital elevation just because there's no longer leaves and foliage in the way. So really quickly, how does this work? Basically, you get an elevation model as we see on the left. In our cases, we have been very basin centric, and that makes life a little bit easy, or makes life fairly easy. But you don't actually have to be constrained to the basin concept. But in here, we utilize the basin to decrease the amount of data that we have to pull from remote locations. And so that allows us to go through and do a soils recharacterization relatively rapidly. We get the DEM, we get all the information from the broker, and lo and behold, oftentimes local. And I'll show you two cases that we're using. Either we can do a local soils recharacterization to give us basically a starting point for going out into the field and setting up our new projects. So one of the things we wanted to do is test the reliability of this as an automated system. And but we didn't have much funding for it, so we picked smaller areas, and a place with 55 USGS stream gauges exists down in Puerto Rico, and within a relatively small area. So we decided, what if we just automate this process and give it a whole bunch of starting points? Can we build up the full recharacterization of the watershed automatically? And we had a success rate of roughly 50 out of 55 of the basins, but no, we could automatically extract all of the information necessary to build any of these models off of. There are some artifacts in the automatic subbasin delineation algorithm, so there is probably still value for a human in the loop there, but that is only if it fails. Otherwise, if it's not a straight up analytic or a straight up computational error, then lo and behold, it should be accurate. We also have interfaces to other packages. So we are currently, these workflows are heavily written in, are primarily written in R and or Python. We keep two different versions of them. The Python side allowed a quick interface into the ArcGIS interface. And lo and behold, we implement that just as a toolbox. And the other stuff that you had seen was all implemented in R, run and implemented in R. Something I wanted to do now that that part is over is obviously the rapid characterization is also useful in prediction for forest fires, but that was not the topic of this session specifically. But lo and behold, the getting as much data for an area is very important for being able to predict where fires are going to be dangerous and what issues might have. So in conclusion, we're really on the last months of the porting between the brokers. It is operationally used by watershed modeling communities, specifically the SWAT variable source area, which is a higher resolution sub field scale watershed model implementation. And the purpose of this was actually would like to find some use cases outside of just variable source area water quality modeling, and say the topic of this. And really, from there, I also have to always throw in the plug if we're talking about new data and being able to integrate new data. The brokering system, as James in the crowd can also attest to, is we're working towards, can we, when we actually build very rapidly prototyped instruments, can we get that data also into the brokering system here? And so this is one of the, these are some of those toys that we play with to get more rapidly get more information on weather, soils saturation, and even bio portions with our little horse there. And with that, I will leave it to you, yield the floor.
Not. Just a comment, Daniel. So you're looking for use cases. So it seems like the next speaker, Dahlia's, could be a use case for what you've done. So so that's the both Kathy's and Daniel's talk is talking about the effects of on the landscape, on the ecosystem from fire. So Dahlia Kirschman from Goddard would talk about kind of the consequences or of those effects of the soil, consequences and also subsequent and consequent effects on the hazard susceptibility, in particular landslides and debris flows. Dahlia.
Yeah, thank you so much. I'll keep this short. I know everybody's probably pretty hungry, but I'll just preface this by I'm not a wildfire expert, and I'm not actually even a post-fire debris flow expert. So this is really new territory for where we're going. And so I think, as Bill mentioned, this leveraging kind of the data products that were presented by the last two speakers, I think has a really, really interesting opportunity to advance some of this work. So what I'd like to do today is kind of give the 10,000 foot view and kind of show where this may fit in the future. But just to get everybody on the same page, we've been talking about the impacts of fires. I'll stick with what I know, which is more, the byproducts. So what is a debris flow? You know, it's similar to a landslide, but as we heard from previous presentations, you know, the hydrophobic nature of the soil once an area has been burned and then there's an increase in sediment, both causes a lot of runoff with respect to debris following major fire events. And it obviously happens in varying degrees, you know, depending on the severity of the wildfire. And so there's a lot of different impacts that we can observe. We see them routinely after every fire season in California. We'll definitely see them in Australia, unfortunately, as well. But I mean, you can just see some of the examples of how kind of these debris flows can rapidly inundate an area. So the left image is a pre and post, I think 7 hours apart of what these areas look like, and they can rapidly affect a landscape. And so we've been working with the USGS Landslide Hazard Program to better understand this and how we can take this very local scale impact and approach it in a much larger perspective. So the USGS is the lead in the United States for focusing on debris flow hazards from the federal side of things, where NASA is much more on the research side at this point, and will continue to be that way. But they do have a pretty great system that they've developed. It's a Esri map that highlights some of these post-fire debris flow assessments that they've done, and so this is publicly available. So just kind of zooming in on one, I just selected Douglas County, Oregon, from a fire that happened last year. And so what they do is they have a methodology that looks at a couple of the different characteristics that we heard about before to basically estimate the probability of a debris flow in percent based on a certain amount of rainfall. So with this, it's 15-minute rainfall intensity, or a 15-minute rainfall intensity of 24 millimeters per hour. So and so they do these after many of the large fires to get a sense of what may happen after the fact. But other than this, there is no systematic routine debris flow monitoring going on in the US at all. So our question at NASA is, how can we take something that's extremely local, basin specific, even sub-basin specific, requiring a lot of detailed in situ information on the soils, on the burn severity, et cetera, and scale that up to something we can approximate globally. And so we're going into a lot of different uncharted territory for us, but the way that the place that we are at NASA is we have been working to develop a global landslide hazard assessment model that's currently running routinely at NASA and used by partners around the world. And so the goal is to advance that system to incorporate the impacts of fires in a dynamic way. And so what you're seeing here is actually the distribution of a 10-year inventory of landslides triggered by rainfall, and the size of the dot indicates the number of fatalities associated with them. And so we've been using this as one of the validation tools to better understand rainfall-triggered landslide hazards. So so just to give you a quick background about what I really know about, which is landslide hazard globally, we've developed a model called the Landslide Hazard Assessment for Situational Awareness, or LHASA model. It's currently in version 1.1, I guess. It's an open source Python-based model that's fairly simplistic. It uses a decision tree structure. We've calculated static susceptibility based on slope, land cover, forest cover loss, distance to fault zones, distance to road networks, and rock characteristics. And we couple that with satellite rainfall from the Global Precipitation Measurement Mission. And this is the multi-satellite product that we have. It's available every 30 minutes at a 0.1 degree or 10-kilometer resolution. And so you can see on the right, we go through at this point a simple decision tree approach where we look at the past 7 days of rainfall in an accumulative sense with a dry down curve. If that is high, which we define as the historic 95th percentile, then we look at susceptibility. If that's high, then we either issue a moderate or high nowcast, and that's available every 3 hours from right now 65 degrees north to south, which is the resolution of the extent of the rainfall product. So what we can do is we can start to look at this retrospectively. We can look at how landslide hazard season is changing around the world. And again, this is absent of wildfires at this point and absent of seismicity, which doesn't really have a season, so it doesn't make sense to include. And so you can start to see the distribution of how things are changing. And this is actually the first kind of global analysis that's done like this using 20 years of precipitation data and susceptibility information. And so you can start to see patterns, not just in our model, which we call, nowcasts, but also you can look at the distribution of our inventory that you saw before, and it kind of shows the hotspots, but it also highlights areas where we may be completely missing the landslide hazards or the reports based on our limited reporting, which has all been based on media reports thus far. So, okay, so how do we want to advance, and why is this at all relevant to this session? Well, we know that after a fire, the landscape completely changes, and so the application of our model doesn't really make sense. We have to treat it differently, but the question is how. And so this is very much in progress. It's actually at the very beginning of the process, but what we're trying to do is we're trying to take the rainfall data, the satellite precipitation information, look at the high intensity short duration events to see if we can even get that kind of critical rainfall that the USGS identifies in these types of environments. And we don't know if that will work. We then want to look at the MODIS-based burn severity or locations of past fires to get a sense of how we can extract some of these characteristics of the fires to see if we can, put that into a model. And then if all of these are feasible, build a post-fire debris flow model that may better represent conditions on a landscape following fires, and then implement a recovery to that as well. So I'm very interested in the previous speakers talk about recovery. And so kind of going to these three questions, again, we haven't done any of this work yet, so it's kind of at a funny stage to present it, but one of the challenges with satellite information is that, with the Global Precipitation Measurement Mission, it's a constellation of satellites anchored by the GPM Core Observatory, but if there isn't a microwave overpass of a really intense convective storm, we're going to miss it, or we're going to miss the peak intensities. And so the question is, in fire areas, they really care about peak intensities with short events. So we may completely miss some of these critical events, and so how do we account for that or not? So that's the first question. I'm leaving you with a lot of questions and data needs versus answers and solutions at this point, sorry. Can we use satellite information to identify burned areas that are likely to cause debris flows? So that also gets into kind of characterization of catchments, characterization of burn severity, and I think the answer to this question is more likely yes, but we're starting to go down and understand kind of how this is done globally. And I have to, as we were doing a lit review kind of leading up to this, not this meeting, but kind of this work, the only real data sets that we have are for the Western US, and those are developed by the USGS and other research groups, but there are not global data sets of post-fire debris flows that are public. And so this is a huge gap in understanding kind of this relationship between where are burned areas and where are post-fire debris flows, because we don't know, or we don't have the data to show it. And then going to this topographic question, which was brought up before, is do the DEMs that we have globally suffice to kind of characterize this upslope area of, debris flow movement? And, 30-meter DEM is fine, but, to what extent can we approximate kind of higher resolution kind of material, patterns in movement, and ultimately get to exposure? So what's happening downslope? And so depending on the resolution of the model, you can answer different questions about hazard and risk. All right, so there are several different ways to go about this. And so I just give three here. The right two are published. So one is a logistic regression model, which is based on Dennis Staley's work at USGS, and that incorporates burned area or percent of burned area with high slopes. It looks at rainfall maxima of 15 minutes. It looks at the burned ratio, and then the soil K factor, which is a function of kind of how water gets into the soil. And so it uses a regression model. It's been calibrated in California and then applied across the Western US with pretty good success. But the question that we have in working with them is, can we do this globally? And that's kind of like I don't know. And then the other is something we've been looking at with a researcher in Florida about using machine learning, another theme, for post-fire debris flows to look at how we can advance some of these kind of non-parametric statistical techniques. How do we represent these in areas where we don't have data? And then the thing that we're starting with is the very basic, like, did it burn? Is it steep? Is it raining hard? And if we can start to do that, maybe we can compare these more sophisticated models to this very simple model in the Western US and see how good we can do. So as I said, we have LASA 1.0, but as part of the disasters program and a funded project through them, we're moving towards LASA 2.0. And so this is kind of right now our current plan, in that, you know, we'll still be incorporating static factors as well as dynamic factors, both rainfall, soil moisture, and earthquake impacts. And then the fire module will be separate. Basically, like if it burned, treat everything differently. And so that's kind of what we're trying to figure out now. And so we're using a machine learning based model, XGBoost. And so the goal is to develop a probability of potential landslide hazard and then use that to get into risk and exposure modeling. So that's our plan. And so that's where the fires fit in. So this is my last slide. I mean, I think that, you know, Bill asked us to kind of focus on data needs. And so I would love to be the recipient of some of this really cool new research and trying to, you know, take these very local models, these very local data sets, and extend them to larger areas, because that's really what we need when we're trying to do global work. So in terms of data needs, and kind of, I like this figure. So we first want to know burned areas. So dynamically characterizing the extent of the burned area as a severity. I think we can do that with remote sensing data and update it at a reasonable time period. Soils data is always really, really hard and usually pretty bad. So globally, how can we approximate these kind of soil conditions in a way that makes sense, if not super, super accurate? Rainfall, again, high resolution, short duration rainfall, not so easy with satellites, but are there other things we can consider, level 4 products, model products, that would help us get to that, or statistically kind of represent those potential impacts? And then topography, you know, we have 30-meter data globally, that's fine, but, you know, in getting into kind of the catchment and lower level, you know, to what extent can we increase our DEMs to better understand kind of this situation at a catchment level and infer exposure and risk. So I think that's it. Thanks. I don't think I've ever given quite a presentation where we haven't done any of the work yet, but it's kind of fun.
This is Dave Jones. This is really good stuff. I was just wondering if some of the data needs that you have, is there a way that you can boil it down to maybe data collection requests from maybe firefighters in the field? Like when they're raking up afterward, can they like take a picture or something that might help you? Or is there anything anybody can do that can help you? You know, I mean, they're carrying all this equipment anyway, so it might not be possible, but you know, Catherine, who we're working with at the Weather Service, you know, it's like, here are the things that we need. You know, we need the soil conditions. We need, you know, because it totally changes their flash flood guidance in real time. So I'm just wondering if any of these data needs that you have might be collected by in situ measurements or something that where people are in the field. Maybe the Forest Service can say, oh, we can do that. And, you know, USGS says, yeah, it's not too much of a stretch. We can kind of get that. Just wondered.
Yeah, no, it's a great question. I mean, I think domestically, you know, we really look to the USGS and Forest Service to kind of provide some of this, but the biggest gap is past inventories, right? So we can only validate our models so well if we only know how it is. And unfortunately, we have a lot of different approaches, like machine learning approaches for mapping landslides, but mapping debris flows on burned soil is really hard. It's not really feasible, right? Like everything looks the same. It's all brown. So I think, I mean, I'm not a soils expert, I'm not a fire expert, I'm not a post-fire debris flow expert, but I would say that for the community at large, more inventories are going to be the best start, because you can always kind of go back and do in situ assessments, I think, for some things, but the perishable data, soil conditions, and the debris flow, kind of the situation of what's happened, I think is critical. Yeah.
Just a comment. So the 4 talks, right? It's partly by design that as we get to the 4th one from the first one, it gets closer and closer to Dave's and Karen's cluster interests. So so even though it may be funny in the way you describe, you know, talking about something you haven't completely done, it's exactly what I was looking for because it gets us to the kind of the potential collaboration with the
Right.
disaster cluster.
Yeah, I mean, and I think, going back to a thing that I know a little bit more about, which is like global landslide hazard assessment. I mean, our models are operating routinely, not operational, but they're operating routinely right now. And so I think that, we're iteratively improving upon those estimates, and wildfires is just a big gaping head wound that we haven't addressed yet. But I think that overall it's helpful. I mean, this is the only system that exists globally, so it's helpful to know how we can take what we have, benchmark it, define ORLs with it, and then start to iteratively improve with feedback. And so that's where we're going with the disasters project, but that's like kind of the holy grail of trying to make things better. And everything's going to be open source, which is why I asked you guys the question earlier. It's open source, so there's just a lot of opportunity for improvement.
Yeah, no, that's great, because then we can take with the community that we're putting together in disasters life cycle with the All Hazards Consortium,
Mm-hmm.
we can utilize GeoCollaborate to get the products in front of
Right.
Catherine at the Weather Service.
Yeah.
Somebody else at the Forest Service, somebody at CAL FIRE, so we can really, not waste time and put things in front of people and say, hey, does this help?
Yeah.
Here, it's an ORL4 right now, but does it, can you assess it?
Mm-hmm.
Are you interested in it? That way we can give you feedback and you can say, hey, we're getting interest from CAL FIRE. And then you can say, oh, here comes more money,
Yeah, yeah. And I mean, and there are things that we've talked about. So right now our model's at 1 kilometer, and it'll stay at 1 kilometer for the public release. But, for specific partners, there's no reason why we can't go higher resolution as long as they're trusted partners, because there's a lot of sensitivities there for a lot of reasons. But that's a great opportunity if it's kind of within a kind of the correct group to provide feedback on the higher resolution versions. Because that's what we hear from like the DoD side. We need something at like city block scale. We're like, well, we can kind of do that, but we can't share it publicly because that's for a lot of reasons.
Hey, Delia, I learned something a couple of talks ago about, I saw for the first time that fires can alter the absorption ability of water.
Yeah.
Hydrophobicity, I think is.
Yeah.
So would your model, is that too fine a scale information? If you're just talking about 1 kilometer resolution, I don't know what,
Yeah.
the effect, how wide the effect is of hydrophobicity is.
Yeah.
Is that too fine a scale for your model? Or
I mean, I think that there are ways to represent it like as a proxy. Again, not a soils expert. So the remote person who talked about that, yeah, she can talk more. But I also found out from our USGS contacts that hydrophobicity changes based on like what they were saying is in California, we just assume that that's the case for post-fire debris flows, but there's a lot of waxy plants. And so part of that hydrophobicity is actually like caused by the melting of all these waxy plants that creates that surface. Again, this is not my area of expertise at all.
I
but in
it for
other
the first
areas,
time,
so for the Pacific Northwest, for example, the fire signature has a very different impact on debris flows. And so I don't think that in this next version of that thing, we're going to be able to resolve that. I think we just basically want to know, like, just treat it differently and then try to figure out kind of how good we can do. Because right now, the only places that this is applied is over kind of targeted areas in the Western US. So we need to be able to do this globally at some point. But yeah, that factors into kind of the soil K factor,
Right.
which is what we have to figure out how to do.
Hey, Kathy, do you want to comment on that aspect?
Yeah, so I will preface this with the comment that I'm a modeler and not an empiricist. But I would expect the KF factor, just looking up the definition, to change with fire. So what you're pulling from the data sets for a particular soil type classification is probably not going to be representative of what the actual KF factor is after the fire. That being said, because of the model structure that you're using it in, you might still be able to get some information, because it's a sort of a summary of how the soil was beforehand.
And I have a related question. So what is the effect of the intensity of the fire on the degree of, I guess, hydrophobicity changes?
Yeah, so typically hotter fires produce more hydrophobicity, just as a general rule of thumb. We were earlier talking about what people with boots on the ground could measure, and it might be interesting to have someone pull up a soil core and drop water on the top of the soil and see how quickly it's saturated into the soils. And also bulk density, so volume, mass to volume measurements would also be something that might be informative to one of these models. Yeah. So that does answer your question, and then it rambles off into another tangent.
Yeah, I was also wondering about the depths of the hydrophobicity.
My understanding is that it's typically surface. And that's one of the reasons why it's also a sort of a temporary condition. It's very ephemeral from what I understand. So, yeah.
Okay, yeah, thanks. Any question for any of the speakers? Online?
I would like to ask the group, and this is actually related to just what the prior conversation was, is with the soil KF factor as well as in watershed modeling. A lot of watershed modeling is just based off of the NRCS curve number approach. All of these things are stochastic in nature. All of these indices are stochastic, and they all get reset. The prior models no longer are valid when it was a stochastic model before. The same thing creeps in with the machine learning, but the machine learning allows a much more rapid readjustment of state. But how do we trust the machine learning? And I believe that we should trust the machine learning because it's a very valuable tool, but we also need to verify with more physically based models. So how do we go about trusting and verifying, I guess, is the question that I have. How do we take our knowledge and make sure that the answers will be constrained to something that is believable yet predictable?
James, you want? Yeah.
So then, how do we trust the machine learning model? That's a really tough question. And so the way that I've tackled it in my own work is, it sort of depends on how big is the model, what kind of model is it, what kind of layers are you using. But with small models, you can kind of do what I did and just inspect the model and look at the weights and stuff like that. And, are the results that you're getting make sense in the context of like physical reality, right? So are you pulling out patterns where these things make sense? And so that's easier to do on smaller models than it is on larger models. And this gets even kind of crazier when you look at natural language processing models that could be hundreds of millions of parameters. You can't really inspect that in the same way that you could on a smaller model. But there are other methods. There's been some good work with competency. So it's like a neural network will give you a classification, and it will sort of tell you how confident it is for that particular classification. But what it doesn't really tell you is how sure is the model that it came to that particular result. And so there's this idea of competency. Given an answer, how sure is the neural network? Not just like what's the output of the the softmax layer or whatever, but is there any other metrics out there that can be used to figure out whether the neural net's sure or not? And there are some techniques out there for doing that. And it really comes down to analyzing weights and being intelligent about it. But the main thing that I think it boils down to is just, large scale verification, being able to look at a whole lot of data and a whole lot of results, and then bringing in the scientists or bringing in the experts to be able to look at these things. And so when I did my project, it was like, we had workshops with the scientists to actually look at the results or say, does this make sense? Is there any link to physical reality here? And so you basically just have to do your due diligence there. Did I answer your question well enough?
I think we're now preaching to the crowd. That was a bad question because I think probably we're now in agreement with that.
Yeah.
So anyone else want to take on the questions of, or I want to actually point out that very related to what we were talking about today, the snowmelt models, most of the snowmelt models out there are temperature index based, and they get completely reset. And as far as post-fire hazards, the snowmelt events are one of the major drivers for risk-prone areas.
Would you happen to know if those snowmelt events are responsive to the smoke sedimentation or the fallout from the ash and the smoke that you get from the plumes there? Is that included in those models at all?
They are not included in in the traditional models that are currently being run. They are included in some of the research models that have been published. In fact, I have a publication on that in itself.
Hey, Daniel,
Indeed.
do you want to follow up on this in one of our next coming up telecoms? Because I think that would be a good. We are running just a couple of minutes over now, and so I think it would be good to follow up on this in one of our monthly telecoms. Do you want to do that?
Indeed.
Yeah. Okay. Yeah. So yeah. So before I wrap up, I just want to thank all the speakers. It's both remote and here. So for me, I think we got what we aim for to do this session, which is connect all the 4 speakers and eventually aiming towards the disaster cluster. So I think I'm just going to skip my wrap-up slide. But we are aiming towards July, Easter summer meeting, to have a more extended discussion. This is really touching the surface, and to explore some of the connection between all these 4 topics, and also even before James's, right, in time, even be like forecasting fire from say soil moisture, and also connections with the disaster cluster work. Okay, thank you very much.